Welcome to the Explainer. Have you ever wondered why something simple, like a metal rod, can suddenly fail in a really catastrophic way just from a simple twist? Well, today, we're diving deep into the hidden world of principal stress and strain to figure that out. This stuff is an absolute cornerstone of mechanical design, and we're going to break it all down.
Okay, so here's our game plan. We're going to start with a pretty puzzling engineering problem, and then we'll build up the core concepts from there. We'll even get to know a really powerful visual tool that makes all the complex math feel like a piece of cake. Then we'll get our hands dirty with some real-world problems, and finally, see why all of this is so crucial for predicting when things are about to break.
All right, let's jump right in with a question that, has been a real head-scratcher for engineers for a long time. But don't worry, by the end of this explainer, you are going to have the answer. You'd think twisting a shaft or bending a beam would be pretty straightforward, right? Well, it turns out the real story of what's happening inside that material is way more complicated. Deep down, there's this complex battle of forces raging, and what we see on the surface, that's just the tip of the iceberg. So you've got this chaotic mix of stresses all happening at once, and that means the real danger zone, that point of maximum stress, might be totally hidden from view. So, how in the world do we find it? Well, the key is to zoom in, way in, to a single tiny point in the material.
So, to make any sense of this mess, we're going to isolate a teeny tiny imaginary cube of the material. A good way to think of it is like a single pixel in the huge high-def picture of stress, and we call this little guy a stress element.
Okay, so picture this tiny cube. It's being squeezed and stretched from all sides, right? The forces that are pushing or pulling straight on its faces, we call those normal stresses. But at the same time, there are forces trying to slide its faces past each other, and those are shear stresses. It's like the material is being pulled in a tug of war while also being distorted. Okay, now this is where things get really interesting. The amount of stress we measure actually depends on the angle we're looking from. It's kind of like looking at a sculpture from different sides. You see completely different things. So our mission, really, is to find that one specific angle that reveals the true maximum stress. And that brings us to the big aha moment. This is the whole reason we're here. We're talking about the concept of principal stresses.
So, what if I told you that we can rotate our little stress element to let's call it a magical orientation, where all those confusing shear forces just disappear? They go to zero. And what you're left with is just the pure push and pull stresses, and they happen to be at their absolute max and min values. Those are the principal stresses.
Whoa, okay, I know what you're thinking. A big formula, but stick with me here. Don't let it scare you. This thing is basically the mathematical key that unlocks the whole puzzle. You just plug in the normal and shear stresses that you already know, and this formula will spit out the absolute maximum and minimum stresses for that point. It's like a secret code for predicting failure.
So that formula works, for sure. But it's not exactly intuitive, is it? Well, luckily for us, way back in the 1880s, this brilliant engineer named Otto Moore came up with a way to turn all that complex math into a simple picture. It's called Moore's Circle, and honestly, it's an engineer's best friend.
So you want to see how to draw this incredible map of stress? It's actually a surprisingly simple step-by-step process. Let's do it. And just like that, with those 4 simple steps, you've created this incredibly powerful visual tool. You see, every single point on the edge of this circle represents the state of stress at a specific angle. It's literally a 360-degree view of all the forces happening inside your material. And here is the magic of Moore's Circle. This is why it's so cool. The principal stresses, the very things we've been looking for, are just sitting there, right where the circle crosses the horizontal axis. And the maximum shear stress? That's just the radius of the circle. All the answers you need laid out in one simple, elegant diagram. It's incredible.
All right, theory is great and all, but let's see how this stuff actually works in the real world. We're going to get our hands dirty and tackle a couple of problems from some engineering certification exams. This is where the rubber really meets the road.
Okay, so here's a classic problem. We've got stresses acting in 2 directions. But notice something important here. There's no mention of any shear stress. So what's the maximum principal stress? Let's figure it out. So, did you spot it? This one's actually a bit of a trick question, but it's perfect for showing the concept. Because there's no shear stress, we're already looking at the principal stresses. The element is already in that magical orientation. So the maximum principal stress is just the bigger of the 2 numbers. 200 MPa. See? Easy, right? Okay, let's flip the script a bit. This time, we're actually given the answer, the Moore's circle itself, and our job is to work backwards and figure out what it tells us about the material's strength. This is where you can really see the power of this graphical tool.
First things first, we just have to, well, read the map. It's all right there for us. The principal stresses are where the circle hits that horizontal axis. So that's -10 and -100 megapascals. The max shear stress, that's just the radius. A quick calculation, and boom, we get 45 megapascals. Pretty straightforward.
And now for the big payoff. There's this rule for materials that stretch a lot before they break. We call them ductile materials. The rule says they'll start to permanently bend or yield when the maximum shear stress inside them hits half of their total yield strength. So we just double our max shear stress of 45 and we get a yield strength of 90 megapascals. And that's it. We just used a picture to predict material failure.
So, we've learned how to find these maximum stresses. We can draw the circle, we can do the math. But now let's go back to that big question we started with. Why does any of this actually matter?
Here's the final piece of the puzzle. It all comes down to this. Different materials break in different ways. You've got brittle materials, like glass or cast iron. Think of them like a dry twig. If you pull them too hard, they just snap. They hate being pulled apart. So for them, the maximum principal stress is the killer. Then you have ductile materials, like steel. They're more like taffy. They stretch and deform. They fail when layers slide past each other. So for them, the maximum shear stress is the thing to watch.
So, let's bring it all home. By finding these principal stresses, we can cut through all the noise of complex forces and find the true danger points inside a material. This gives us the incredible power to predict how and when things will fail. And that knowledge is absolutely essential for designing everything from a massive bridge to a simple paperclip safely and reliably.
So we figured out how to find the maximum stress. But that brings up the next big question, doesn't it? How much stress is too much stress? Well, that is a topic for another explainer. Thanks for joining me on this deep dive into the world of stress and strain.